This is a delight for me to share my love for galactic ecosystems. And so let me get started with a little thing from the preface, which kind of gets us started. It's not an exaggeration to state that galactic ecosystems have spawned pretty much everything that we hold dear, including ourselves. These nebular nurseries have incubated all the stars, planetary systems, and many of the complex molecules known to humanity. From there, the myriad of planets in orbit around their hosting stars have further refined the organic matter into even more complex biochemicals. On the surface of one particularly moist planet, life took hold, and evolutionary processes led to you and me collectively pondering the wonders of these galactic ecosystems. So my charge today is to try to define what a galactic ecosystem is, to show where they are located in our Milky Way galaxy and in other galaxies, and to also hint at the possible chemical pathways that are going on within those galactic ecosystems and into the smaller things, the preplanetary systems as well, that at least in one instance led to you and me. Okay, so that's my charge, and I hope you accept it. So if I will begin with this supposition. What if we could leave Earth and so behold the entire sky at once? So what do I mean by that? Well, you get on a magic carpet, of course, and you leave Earth. You've had enough. You know, you're not happy with it, maybe, or maybe you just want to go for a trip. And you go, but you have to go far from Earth so that it's not obscuring half of the sky. And then you want to get it far enough away from the sun so that it doesn't blot out half of the sky. And so imagine yourself that you've figured out a way to get sufficiently far from the solar system so that you could look around, and what would you see? You would see the Milky Way completely surrounding you, all around. It would enfold you in its beautiful light. So in mapping this, you end up getting something like this. This is an all-sky map. How was it made? Well, it was made from the surface of Earth. You had to go take a bunch of pictures from the northern hemisphere, and then you had to take a bunch of pictures from the southern hemisphere and then stitch them together, which is what Axel Mellinger did, I think about it more than a decade ago. And you can see that the visible view of the Milky Way is not this perfect scrim of starlight, but there's details. And a lot of the details involve dark regions, which we now know consist of clouds of obscuring dust and associated gas. And then there's these luminous regions, also the starlight. There's the starlight, which the clouds are seen in silhouette. But there's these roseate regions, these rosy regions, which we now know to consist of another phase of matter. It's ionized gas, ionized hydrogen in particular. And what we can see here, I'll give you some details. This is another galaxy, the Large and Small Magellanic Clouds. And then there's the Orion star forming region here. And what else do I need to tell you?
Could you say on the right of the oval or on the left?
Yes.
Because I can't see you
Yes,
online.
yes, okay, yes. I'd rather not use the mouse. I do it rather talk. You're right. On the right-hand side, rightmost side, there is the Orion star forming region. There's in the middle right, there are red regions, which can also be seen in the middle left. And these red regions are actually indicating regions of recent massive star formation, where the massive stars have ripped apart what was once molecular gas, molecular hydrogen mostly, and then taken the individual atoms of hydrogen and ripped off the electrons. And as they cascade back down to their home bases, they emit a series of emission lines one of which is this red emission line. It's called H alpha. And so that's what we can see visibly. This is what we can see in the far infrared at wavelengths almost 100 micron is like the thickness of a human hair. So these are much longer wavelengths, and you can see that it's a very different scene. The Milky Way does look a lot thinner, and this is a fairer representation of the disk of our galaxy, seen edge on. We're in the disk, we're a part of it, or we're kind of like a mote of pepper in a fried egg. Maybe before it congealed, so you could look through it still. Mike, I know you're getting hungry. And it also shows regions of star formation. All this is dust that has been warmed by newborn stars, and they're re-radiating their warming feelings in the far infrared. Like you and I, we radiate in the mid-infrared at our temperatures. The large and small Magellanic clouds also have star formation, and that is shown here as well. So that's another way of seeing what the Milky Way is made out of and where the star forming regions are. These star forming regions are what I call galactic ecosystems, because I believe that the word star forming region does not tell enough of the story. There's lots of dramas taking place within these regions. So, okay. Third question is, what if we had big enough noses? Mine's fairly large, but I'm talking about much larger noses so that we could smell the galaxy. You're talking about clouds of gas and dust, and would they have an odor? And the bottom line is, yes, they might smell like a chemical refinery, or toast, or the back end of a diesel bus, or maybe a nicely charred steak. So that's just one aspect. It might have many other odors, like of alcohol. So I promised that I would define this thing called galactic ecosystems. So let's begin. They are self-gravitating regions. They're discrete regions. Michael talked about in your written promo, you said that the Milky Way itself is a galactic ecosystem. And the phrase has been used in that regard by several authors. But I am talking more specifically about individual self-gravitating regions of gas, dust, and newborn stars. Cradles of creation, or what I call crucibles of creation. So you can talk about molecular clouds, giant molecular clouds, these things called H2 regions. Those are those rosy regions of ionized gas that have been set alight by the hot stars they're in. And then on a more extreme scale, starbursts, where you're going to get not only the effects of massive stars, but the ultimate consequences of massive stars when they blow up and create super winds. So there's all that going on, which is shown with stellar feedback. You've got the ultraviolet radiation from these wicked hot stars. Our sun has a temperature of 5,800 Kelvin. The hot stars have temperatures of 30,000 to 50,000 Kelvin. So they're real barn burners. They also emit very mighty winds that can push things around. And then ultimately they die. And it doesn't take long for them on an astronomical scale. It might take a few million years. They go through their life cycle, and then they blow up real good. And that moves things around an awful lot, and also creates very high temperature gas. So you can transform the architecture of the galactic ecosystem while transmuting the chemical makeup. Then finally, biochemicals, which I hint at and can't give a final answer as to what's going on in these regions. But there are biochemicals for us. They play key roles in sustaining life on Earth and perhaps elsewhere. So on Earth, water is a big deal. It's a solvent, H2O. Formaldehyde's important, H2CO. Molecular oxygen O2 is obviously important here on Earth. It's what we're energizing ourselves with right now. Methane, CH4. HCN is hydrogen cyanide, which is a poison for most of us, but it may be an important building block for creating the more complex molecules, as is ammonia, NH3, and phosphates. Those are what go the ends in the HCN and the NH3. Those go into amino acids, which go into proteins. The phosphates, PO4, go into the structure of nucleic acids, not too shabby, and so nucleotides. So these are the biochemicals we're familiar with, and lo and behold, they can be found in galactic ecosystems. So enough text. Let's take a look at what we can see visually and in the far infrared. And I'm going to just parse the Milky Way into pieces, which are around 100 degrees in longitude by 60 degrees in latitude. Longitudes on the horizontal axis and latitudes on the vertical axis. And you can see stars that have been born probably in galactic ecosystems, just starlight, but they've since left their wombs or dissipated their wombs a long time ago. And so what we are left with are very nearby clouds of obscuring dust and associated gas. And some of them can be observed by amateur astronomers. The Pipe Nebula in the above center of the Milky Way looks like a pipe that can be traced with binoculars and from a dark sky, like what we're trying to keep at Halibut Point. And we can also see the H2 regions, these emission nebulae, M8, which is, well, you can see it, it's labeled. That's the Lagoon Nebula, M17, it's the Omega Nebula. There's another name for it, I forgot it. And M16 is the Eagle Nebula, and all those H2 regions are visible with binoculars and with telescopes. So in the infrared, again, you get a thinner scene. The disk of the galaxy resolves into basically the full run of regions that are forming stars. There seems to be some stuff well above the galactic plane, and that's the Rho Ophiuchus nebula above the Milky Way plane, and then the Corona Australis molecular cloud to below the plane. And but the scene is muddied by the fact that there's extreme brightening towards the galactic midplane. Is there a way you could kind of get rid of that glaring situation? And so maybe lower the color temperature. No, I'm just kidding.
More glasses.
What you can do is this is all taken from the infrared astronomy satellite survey of the Milky Way, entire sky actually. And what you can do is you can medium smooth the scene, what you saw before, with a window that's has a lot of horizontal dimension and very little vertical dimension. And so this just kind of goes along and takes the average within that window. And so that preserves the midplane brightening, but very little else. And then you take that image and divide it into the original image, and lo and behold, you get this image of residual emission. It's a process called spatial filtering, and it brings out the enhancements and diminutions in emission from the dust in the Milky Way galaxy. And besides this fascinating froth that's everywhere, and you can see patterns, you know, I can see shells here, to the lower right, and maybe a shell to the lower left. And, you can go crazy finding patterns, and I'm sure Alan could find lots of patterns here. But you can see also that these nearby star forming regions, these nearby galactic ecosystems, the Corona Australis below and the Roe Fucus above, they are seen very easily. And also you can see galactic ecosystems within the disk of the galaxy, clear to the far side of the Milky Way galaxy. Good, no, there's a mouse and a half. So I'm just kind of reiterating here at visible wavelengths, these galactic ecosystems manifest as dark clouds of obscuring dust and gas. Those are nearby because they have to silhouette the starlight that's behind them, along with glowing red regions of fluorescent ionized hydrogen gas. Those are the H regions. And then at the far infrared wavelengths, the spatial filtering reveals the galactic ecosystems as glowing regions of star-warm dust, along with a fractal froth of filaments and shells. And if you look at those filaments and shells, you'll conclude, perhaps wrongly, but that they've been messed with, interstellar consequences of prior star birth and star death activity. So to model all this, I've got a cartoon for you. A lot of it depends on the size of the galactic ecosystem. So, but in general, they all start with cold molecular gas and maybe a halo of atomic gas. But inside where there's stars forming, you get energizing, and there's a transition from the molecular hydrogen to the atomic hydrogen, where photons have ripped apart the molecules, diatomic hydrogen molecules. And then there's this transition region, which I show with hatch marks, and that's where the neutral atomic gas is starting to get ionized. The electrons are starting to get ripped off of the individual atoms. And that's the working surface which you would see at that H alpha wavelength. And so that's the result of the ultraviolet radiation producing warm ionized hydrogen at a temperature of around 10,000 degrees. So for a low mass molecular cloud, you mostly have cold molecular hydrogen and maybe a little bit of cool atomic hydrogen. And it's but for a higher mass molecular cloud on the order of maybe 100,000 solar masses, you're likely to get massive photoionizing stars. They're rare, but you end up getting a big enough cluster and you'll get a few. And that will produce a warm region, quote unquote, warm region of 10,000 degree gas, which is glowing in H alpha and other emission lines like oxygen. And then finally, if you have a giant molecular cloud with millions of suns worth of molecular gas, then you're eventually going to have a big enough cluster to have enough massive stars, one of which or more than one of which will have gone boom. And that will produce a supernova, a hot supernova. And so there might be a region within the galactic ecosystem where you have million degree gas, which is exerting tremendous pressures and might even breach the system, producing a superwind. So that's a basic model, which I'm sticking with it.
Bill,
Yeah,
just a real quick question. 10,000 degree gas, does that mean you could toast an interstellar marshmallow? Or is it not really 10,000 degrees there?
it's really 10,000 degrees in those regions.
So you could fricassee an interstellar duck?
Oh, I see what you're saying.
Not enough.
It's the densities are so low.
So it's not really what you expect 10,000 degrees to feel like.
It's that corresponds to the speed of the particles.
Right.
Formula is 1/2 mv squared is equal to 3/2 kT.
Oh, I see. Now I forgot that.
So the velocity goes as the square root of the temperature, or the temperature goes as the velocity squared. So.
So you can have ice cubes in the middle of that 10,000 degree cloud.
Yeah, but they will get, the photons will ablate it at some point.
Right.
Yeah. So, but you mentioned toast, and, the smell of toast, is, some of that is due to polycyclic aromatic hydrocarbons, PAHs, and those are molecules with greater than 13 atoms. This table, you're really gonna have trouble reading it. Don't worry about it. This is the molecules that have been sensed through radio observations, radio telescopes, like the Green Bank telescope, and also in the infrared as well, with other telescopes. They're up to more than 340 molecules that have been discovered in these galactic ecosystems. Many of them, they have favorite targets, which they go after. The Sagittarius B2 molecular cloud near the galactic center. They seem to like that. And then there's a circumstellar disk or something, some circumstellar material around one particular star that they seem to favor in targeting. But there's all sorts of things. And so with two, which, you know, you have to have two, at least two to make a molecule. And so obviously molecular hydrogen's there. And then O2 should be there somewhere. O2, yep, there it is. Okay, and then three, there's the HCN, which I was talking about. Oops, sorry, HMC. There's HCN here somewhere. I can't see, I can't find it. But anyway, that's three, and then four has got the formaldehyde, and you can go on. There seems to be a bottleneck with molecules containing phosphorus, which is kind of a strange thing because our very lives depend on phosphorus for two things. And help me, Mario. One of them is for the nucleotides, and the other thing is for the
ATP.
fats, right?
ATP
ATP,
and ADP
and say it again.
and ADP.
ADP. Okay, those are the energizer bunnies in our cells. And then there's another one, phospholipid bilayers, which is the membranes in our animal cells, right? So phosphorus is very important to us, but it seems to be very underrepresented compared to like carbon. It's down by a factor of 1,000 or something compared to carbon. So makes you wonder about that. So anyway, there's a lot of molecules that they have found. And so I'm going to repeat with this looking towards the galactic center. We've seen the visual with the obscuring dust clouds and the rosy star forming regions, active star forming regions with massive stars. And then here you've seen in the infrared with the discrete galactic ecosystems. They're in the thousands. This particular survey in the far infrared got several hundred, but other surveys more sensitive since they're in the thousands. Okay. So let's start small. And so that's the Corona Australis molecular cloud, which was you saw below the galactic midplane. It's a nearby cloud. That's why you saw it displaced from the galactic midplane. You know, when you get closer to things, whatever deviation they have is magnified. So you can see, you know, there's obscuring dust in a tendril sort of way. There are bright stars and surrounded by gas. This is to the upper right is a globular cluster, which is photobombed the scene. It's much, much farther away. It doesn't belong to the system at all. And even here, this modest region, they've discovered a fairly robust suite of molecules. And I would have to say that the job is not done yet, because in the southern hemisphere, they don't have the sensitive spectrometers on the back ends of the radio telescopes. They're like they do at the Green Bank telescope. But that's like the state of the art. Their spectrometers in the Green Bank telescope in the northern hemisphere. So I think this is a target well worth further study, and I'm going to show a few close-ups. You're now seeing that globular cluster photobombing you on the upper right. But then there's there's this coronet cluster, so-called coronet cluster, which includes a lot of what they call young stellar objects. They're not quite bona fide stars fusing hydrogen in their cores. They're actually emitting light due to their slow collapse and the gravitational energy that gets released. And you might see a few little discrete things with HH in them. Those are Herbig Haro objects, and those are actually jets that are shocking into the surrounding medium. And if we look a little more closely, oops, sorry, I'm done with Corona Borealis. Corona Borealis. I'm moving on to the Rho Ophiuchus cloud. Again, a very nearby star forming region. I love this picture by Adam Block. It's got everything, you know. It's got blue light in the nebula that's from dust that's been scattering light, like the blue sky effect. Red regions because there's some exciting stars right in the middle of in the right hand side one at least. There's another photobombing globular cluster to the lower right, much farther away. And then to the lower left, there's this yellow schmutz. That is Antares, you know, which is in the Scorpius constellation. And it is causing the dust. Well, the dust is scattering light from Antares. Antares has very little blue light. It's a red supergiant. And so the dust is scattering what it can. So those are my explanations of everything. The thick, dark dust regions to the middle center going to the left are shown in blow up here in the mid-infrared, and the green coded emission is from the polycyclic aromatic hydrocarbons at a wavelength of 7.7 microns, mid-infrared. And then
And those are the bus exhaust?
yeah. Or, you know, a charred hamburger would do it. And then the red coated emission is from dust that's being warmed by a star in the center. And they've detected a larger suite of molecules because this one is observable from the Green Bank telescope, so it really makes a diff. And I've got a blow up of this. I think there's kind of like a fan, a little fan here. I'll show that in close up. So there's many scales to these galactic ecosystems, and I think the star forming region just, you know, does disservice to what's going on. Here, the fan to the lower half of the image is basically a working surface of a cavitated region. It's been cavitated by the light from the central star there. And that scattered light, I do believe this is in the, I think it's in the near infrared. And I think this is with JWST, yes. But I want to draw your attention to these Herbig Haro objects, these jets. And description is going to be rough. The biggest jet, I guess, is diagonal, center top to right bottom. That's a bipolar jet, and there's a embedded star where there's, I think, the darkness in the middle of that jet, and it's blowing these very collimated jets, seen here in shocked molecular hydrogen. Okay, so that's one jet. There's a much smaller jet to the upper right. There's a star with a diagonal line, if you will, of emission. It's not very big. That's another one. And then what gets me is in the middle upper part of the image, there seems to be shadow in the thing. There's a star, very bright source. There's something shadowing it. And that is probably due to a disk surrounding that star. And it has blown out some huge jets to the right and to the left, all the way to the right and all the way to the left. So, I mean, that is a magnificent picture. JWST, yay. Okay, where's Phil? There you are. Okay. This is a lovely picture of one of those H2 regions in the direction of Galactic Center. And it shows both M8 and M20, the Lagoon Nebula and Trifid Nebula respectively. And he has used a selection of filters that highlights the ionized hydrogen gas.
Phil, stand up. Phil took that picture.
Beautiful. It's absolutely beautiful. And then also the Trifid Nebula is seen here, both showing ionized hydrogen and then scattering by dust from a star that didn't have the photoionizing oomph like the central two stars that are in the Trifid Nebula, the actual ionized hydrogen nebula. And so that's a beautiful, beautiful image taken from Magnolia, is that correct?
Yeah.
From his personal observatory, not too shabby.
On a good night, well, many good nights, actually.
Yeah. And here is the same scene taken with another observatory, which happens to be one of the greatest ground-based observatories currently on planet Earth, which is the Vera C. Rubin Observatory, located in Chile, isn't that right? Yeah. Which has a big honker camera whose optics are just totally innovative. And so you see the Trifid Nebula where you see scattered blue light all around the region which is ionized. So that's interesting to me. But the lagoon also shows the ionized hydrogen in red. But what's that yellow? And so I've kind of gone back and forth with Mario on this. And what's going on is there's hydrogen glowing there, but there's also oxygen that's glowing there. And oxygen requires more energetic photons to get it ionized to the amount that it needs to be ionized. And the oxygen glows in green. Take red, combine it with green, what do you get? Yellow. So that's my hypothesis. And so far, nobody's argued with me. But now it's recorded, so maybe I'll get in trouble. So I just thought that would be worth showing. Okay, a little more on the Trifid. Trifid is lovely to study because it's such a simple system. It's almost perfectly round. There's just two stars in the middle. And it's bifurcated by 3 dust lanes, which is kind of sweet. In the visible on the left, you see the result, which is reddish ionized hydrogen, and they might have coded for a little bit more bluish in the center, where you had a greater abundance of those more energetic photons. The infrared shows those dust lanes now glowing, and I don't know whether that's again a combo of the green and the red to make the yellow. The green here are the polycyclic aromatic hydrocarbons, and then the red is the star warm dust. So this is just a very nice nebula to study because it's as simple as they come. Here's a better image of it, showing just the ubiquity of the molecular gas in our galaxy. Okay. I think we're done with, well, no. And then there's finally the Lagoon Nebula, And this is a nice picture from the European Southern Observatory in Chile. And you can see that there's a loose cluster of massive stars towards the middle left. And they are doing a job on what was once a dark molecular cloud. It's like little kids screaming and yelling shortly after their birth. And it shows working surfaces to the lower left, which are kind of fun. You see ridges of irradiated dense gas. And I think that's all I'm going to say about the visible region. But here is what you see in the infrared. I think this is in mid-infrared. Yeah, again, the green coating is from the polycyclic aromatic hydrocarbons, and the red coating is from the dust. And there's to the lower left, you see the working surface that was obvious in the visible. So there's a lot to try to understand how the molecular cloud responds to what's happened inside of it. Because there's a lot of destruction, but there may be a lot of construction, stuff getting pushed around, compressed, new stars, new planets. I love this stuff. So, okay, move on. We're going to go look downstream towards the sun's direction of motion. We are all pretty familiar with this section of the sky. It's you can see it in the late summer, early fall, and a lot of us know about Cygnus, the swan, and the triangle. What is it called? The summer triangle, which consists of Altair to the right, Vega to the upper right, and Deneb to the middle. Those are easy naked eye stars, which can be seen from Rockport. And the Milky Way has, again, it's mottled with nearby molecular clouds, and also rosy regions of massive star formation. Okay, so in the infrared, you can see that the Cygnus region is just nuts. There's this region leading up to the Cygnus region in the middle where there was no data taken at the time from the infrared astronomy satellite. So there's a lot to behold here, but I want to draw attention to not only the Cygnus region, it's one of the largest star forming regions within 7,000 light years of us. So a lot to study. The North American Nebula is part of that. It's just part of the near surface of this galactic ecosystem. But there's also a true shell to the middle left. There's this big shell in, oh my gosh, I had a question since we, okay. That is a region which is likely showing propagating star formation. Something happened in the middle of this shell, and it there must have been some explosions, some supernova explosions. It compressed what was available there into a shell, and now we have new stars and planets being born inside the shell. It's a beautiful, almost a textbook case of secondary propagating star formation. And then there's another shell to its left, and they do have names, and I'm blanking on them. That's Cepheus. One of them is Cepheus.
Could you back up to the previous slide for a second?
Yeah.
Now you're talking about Cepheus. Could you point out where it is for everybody?
Yeah, Cepheus is to the middle left.
And it looks like a house on its side.
Yeah.
See the peak of the house on the left?
You don't see a king there, Mike?
Bear with me. Bear with me. The peak of the triangle on the left. That star has two planets, I think, in the Goldilocks zone.
Wow. Yeah, there's several naked eye stars that have excitement going on around them.
Too far.
I will show this with the next set of slides. But yeah, that's a CPS law. Okay. Oh, so, all right. So to the far left are these galactic ecosystems which show up in the star warm dust. They also show up in the red, just above the double cluster in Perseus. Those are the heart and soul nebulae. And here's a close-up in the mid-infrared. And the heart one, I believe, is on the right because it looks like the ventricles of a heart.
The left ventricle is blown out, but yeah.
Yeah.
May that not happen to you. Excuse me. So, this is a lowly image of WISE, I think it was the WISE satellite. And the Soul Nebula is to the left, and they're like separate regions, but obviously this is a very fecund, fertile region. Maybe it was a giant molecular cloud complex at one time, but stuff has happened within these regions. Recently, to the upper right is a very exciting region, which I think is the youngest.
The center of the heart has about 50 new stars.
50 new stars. Yeah, we're starting to get sizes which are, instead of tens of light years, we're dealing with hundreds of light years on the side. So we're getting a lot of action because there's more massive stars. Close-up of the Soul Nebula shows some fascinating structures with these pillars of dense gas and dust, which are capped off by exposed newborn stars. There's two pillars to the lower right, and there's two pillars to the middle left, and those are all pointing towards exciting stars that have had their way excavating this region, courtesy of its very energetic photons and winds, and maybe some supernova explosions as well. And in this study, using the Spitzer Space Telescope, they saw that there was a progression of star forming activity over time. Which way did it go? I think it's going from the lower left to the lower right to the upper left. But don't hold me to it.
Well,
I'm sure it's in my caption.
all those medieval surgeons that cut open all those corpses looking for the location of the soul, what were they way off?
And there's some strange structure to the lower left corner. I wouldn't be surprised if this is shredding by supernova activity. Okay, we're getting through looking towards the galactic anti-center. So this is wintertime here in Massachusetts. There's an error here. It says double nebula. That's the double cluster. I'm so sorry. And the far right with the heart and soul nebulae above it. There's a rosy region called the California nebula. Phil or Mario, have you ever done those nebulae? That nebula, California nebula, and then to the lower left of the California nebula are the Pleiades. So the double cluster is about 10 million years old. Is that right?
Something like that.
And the Pleiades are about 100 million years old. And then to the left of them, the Hyades are 1 billion years old. So, and then all the way to the lower left is the Orion Nebula, which is only about 1 million or 2 million years old. So we have a wonderful succession of sampling stellar populations over time, just looking in this direction. And then, of course, there's Orion with Betelgeuse and a rosy region to the upper part of the constellation, the head of the constellation, which we'll look at more carefully now. But first, the far infrared is fascinating to me Because yes, the California Nebula can be seen to the lower left, lower middle left. But below it is this whole other region, of active star formation, which is just not showing up in the pink. And that's because there aren't any ionizing stars there, apparently. The Orion star forming region, is, is fabulous. It's a 1,000,000-degree molecular cloud, which I'll highlight now, I think. Yes. To the left is the visible view, with that, the head of Orion called Maisa, Lambda Orionis, if you will. It's a double star, two ionizing stars. And there's this whole shell. I wouldn't even call it a shell. I mean, it's like a bubble full of ionized hydrogen gas. Compare that with the infrared, and you see a ring. You see the pileup that the expanding ionized gas has produced on the surrounding molecular clouds. This could be a site of propagating star formation, and perhaps there might be an indication to the right of the Lambda Orionis ring. The Orion constellation is complex. There's different clouds. There's the Orion A cloud to the lower left, the Orion B cloud to the middle, and they all have different ages of star formation. I think again, the sequence goes from the lower right to the upper left. And of course, the star of the show is the Orion Nebula. Any questions on this? It's a lot to take in. Yes, no,
So on the left, those white lines, the ring and the group, those are drawn in, right?
drawn in, yeah, drawn in. It's the constellation. You'd be familiar with the belt stars, in the middle. I would just love to say Alnilam, Alnitak, and Mintaka. It just sounds so, this is a nice mix of names. Okay, so star of the show, the Orion Nebula. My apologies to Mario and to Phil and to others who have tried to take a picture of the Orion Nebula. I mean, I'm happy to look at it just with my eyes. It's bright enough. Never looked through a telescope big enough to see colors, but I've heard that it does produce colors.
It's pretty colorful micro.
Yes, oh, in the 32?
All right.
That's pretty awesome. And this is actually a mix of Hubble Space Telescope and ground based. And I think there's been some color coding. I don't know what the green is here. It could be the effect of the dust obscuration. I just don't know. But let me show you what is probably going on. There's this pocket of clustered star formation, which it has basically overlying gas and dust. There's this thumb that's kind of obscuring.
And that's the bright spot in the middle?
Yes, the bright spot in the middle. Thank you. And I think the red is H alpha. I just don't know what the colors.
The green is really prominent in oxygen.
Is it? Okay, so
It's probably oxygen.
It's a beauty, and if you zoom in with the HSD, you can just begin to see the cluster of stars in the center. It's known as the trapezium. And then there's also this bar to the lower left, this linear bar, which is actually, you're seeing the working surface has curved to an edge-on prospect, so that you're literally seeing in cross-section how the ionizing photons are eating into the once molecular cloud. So that's pretty sweet. And the trapezium itself is highlighted by one particular hot massive star. 40 solar masses is the estimate, 30,000 degree surface. And it has done a number on its surroundings. There are these little squiggly wiggly things that surround the star in kind of green. They remind me of the poor unfortunate souls in The Little Mermaid. Uh, because of the terrible sorceress Ursula. And so those are cometary nebulae. The ionizing photons have eaten into what was once a cloud core and has produced basically a streamer, basically like what a comet does, or what the sun does with a comet, creating this long streamer away from the sun. And these other green things in between the big star and these little blobs, those are shock waves from the winds from the star. So you're getting it in all sorts of ways. And yet, despite all this seemingly destructive activity, inside these cometary nebulae, you can see little disks of concentrated material. To the upper right, you can see a disk seen edge on. To the lower left, not leftmost, but the lower left, there's another disk seen edge on with a protostar in the middle. And to the lower leftmost is a face-on view of,
That's right, most.
I'm sorry. Lower rightmost, I'm so sorry. So, yeah, so the disk seen edge on was lower right, and then lower rightmost is the disk seen face on. And it was a while before we had the resolution to be able to see this stuff. There were papers published which suggested that it could just be all surrounding, but no, stuff that's going into new solar systems is arranged in a pancake with a star inside. That is called a protoplanetary disk, or PROPLID is the acronym. So even in this torrid region, 10,000 degree gas, solar systems are getting themselves together. Okay, last, looking upstream away from the sun's direction. I'm going to focus on the Carina Nebula. Just notice that there is this big region called the Dung Nebula. Apparently, it's possible to see that from the southern hemisphere in really dark skies. I've seen, wow, that's amazing. The Crux I've seen, and that was something my great aunt wanted me to see. She was in a nursing home in having been an Indian missionary for 50 years. She was in a nursing home in Wellesley, and I came and visited her, and she says, "You must go to India and see the Southern Cross." So I did, and it was great. But it's better from the southern hemisphere. Pretty much all this is visible only from the southern hemisphere. Okay, so let's just cut to the chase. The Carina Nebula to the left, middle, is actually a complex of many galactic ecosystems that reside along a spiral arm. So some of them are nearer than others. And I will show that there's possibility that we're seeing an outflow from this whole complex going upwards from the Carina Nebula complex. And here is this complex, seen again in the infrared. There's the Carina itself, but then NGC 3603 to the leftmost is much farther away along the same spiral arm, astronomers think. And so it might not look like much, but it's really one of the largest galactic ecosystems, the most powerful galactic ecosystems. But let's just focus on the Carina Nebula itself. It's a beauty. You can see it naked eye. It's brighter than the Orion Nebula by several fold. It really kind of intrinsically outshines the Orion Nebula by a whole lot. And there you can see it in X-rays. So all that diffuse gas seen in the right-hand side image is X-ray emission from million-degree gas associated with recent supernova explosions, probably within the last million or so years. They're like volcanoes. They don't stick around. They dissipate quickly. And here's NGC 3603, one of my favorites. Huge pillars coming from the middle right and the lower right, huge pillars of creation, they call them, being irradiated like mad near their caps. And then there's this very dense cluster of massive stars, which is pretty obvious. And then there's this one star just off to the upper left called Share 6, I think. And it's literally blowing its stacks. It hasn't gone supernova yet, but it's having an outburst. And so it has a cap to its right and a shard to its lower left, and then a ring around it. Beautiful stuff. Lots of dynamics. And then beyond the Milky Way, there's other galaxies, large Magellanic Cloud at visible wavelengths dominated by the Tarantula Nebula to the left. And you can see essentially the starlight is concentrated in a bar-like situation, but there's many regions of star formation in this small irregular galaxy, about 10 times smaller than the Milky Way galaxy, but it has a lot of gas still remaining to make new stuff. Here's the infrared view of all that, and you can see it's just chocolate block with molecular glass gas, polycyclic aromatic hydrocarbons glowing green in this rendering. And then beyond to M33, the Triangulum galaxy, the Pinwheel galaxy and Triangulum, and you can see a few rosy H2 regions in this galaxy on the left. It's a modest galaxy, about half the size of Milky Way, but it's a spiral galaxy, and you can see the spiral arms. Looking in the infrared with the Herschel Space Observatory, and you can see that the galactic ecosystems, the active ones, are arranged along the spiral arms. So that's and that tells you that the dynamics associated with making spiral arms are amenable to creating these condensations within which massive star formation occurs. Okay. NGC 628 or M74, the Phantom Galaxy, is a textbook spiral galaxy, good size, giant spiral galaxy. It looks like spirals, simple spirals in the radio, that's the upper left, but then in with James Webb in the mid-infrared, there's a whole lot more going on, and it's puzzling. It's not just the spiral arms, but there's stuff going on in between the spiral arms, kind of like cellular structure, which has yet to be understood. And here's a better picture showing what's going on. So it's not just the dynamics of spiral arms that we're seeing, the density waves that supposedly pass through the disks of the galaxy producing spiral structure. There might be consequences of star formation producing bubbles, or it could just be gravity, where the denser regions are getting denser and the voids are getting emptier. We don't know. Tony Weinbeck, who was on my Earth and Space reports often, is studying this. Okay. Finally, the starbursts. This is for Elaine, M82, one of the nearest starburst galaxies with a multi-wavelength rendering, which shows the optical in the green, coded green, the X-rays in the blue, and the infrared in red. The infrared showing dust that's being taken for a ride with a huge from a huge outflow, and the blue is all the hot coronal gas, million-degree gas. And there's a model of it here. We would be seeing it not from face on, but from the edge on perspective. This galaxy is using up its gas and getting rid of its gas very fast. It's a truly dynamic feeder of the intergalactic medium. So I'm going to end with this idea, getting back to the chemistry, and I am not a chemist. I'm not like Steve. But I'll take you on a little trip here. What are the pathways? What gets made in the galactic ecosystems? What gets destroyed on its way to forming protoplanetary disks and ultimately solar systems? What gets made on site in the planets that ultimately form? We don't know. We don't know that pathway sequence. So I'll start to the upper middle to the upper left with the galactic ecosystem, the ionized portion of it. Some massive stars have ionized its Earth cloud. We can see all sorts of molecules there already. That will form in the upper middle a protoplanetary disk with a protostar in the center. And if you follow the arrows down in the middle, you'll get a star, the sun, like the sun, which will go through its life depending on its mass. The more massive ones go through it faster. And the star expires to the lower left in a planetary nebula shown here, which is a source of new dust and molecules. And that, or in a supernova explosion, depending on the mass of the star. And that feeds back into the interstellar medium from which new galactic ecosystems form. Along the way, planets get made around the protostar and stuff gets delivered to the planet. Comets can deliver some kinds of molecules, which are shown to the upper right. And then, of course, meteorites can bombard the planet. And we know that meteorites contain very rich hydrocarbons, and some of them having nitrogen in them, some of them verified as being amino acids. And then maybe on the surface of the planet, molecules figured out a way to create RNA, DNA, and other molecules that can self-replicate and do other jobs. So this is an unconstrained story where astrophysics, astrochemistry, and astrobiology converge. So it's an exciting time for all those folks. And for more information, I encourage you to read my new book, Crucibles of Creation, Exploring the Origins of Stars, Planets, and Life Within Galactic Ecosystems. And I have signed copies available for $30 following the Q&A. But let me just finish with this poem. Michael has poems in the book as well, aided by a lowly assistant. So here we go. But after all, our dreams are all we are. Fine dust from once exploding stars, imbuing breaths with mist set free from nebulae to you and me. So, thank you.